So the next talk is by Arkadev Chattopadhyay from TIFR Mumbai on the power of super-log number of players.
Thanks, Arvind. Thanks, Meena and Rahul, for organizing this fantastic workshop. So this is joint work with Mike Sachs. Okay, so I'll briefly review communication complexity. This has already been done by Shagnik, but a little while ago on the first day. So let me again recap for you. So this is Yao's two-party model. This is the classical model of communication complexity. So just bear with me. I'll be quick with this. So there are two players, Alice and Bob, and they have unbounded computational power, and they want to compute some function f. The function f depends on both x. The function f depends both on x and y. X is with Alice, y is with Bob. So although they have unbounded computational power, they are informationally bounded. Okay? So what they want to do is they want to collaborate in terms of a communication protocol according to which they take turns in communicating with each other to compute this function. At the end of the protocol, both Alice and Bob should be able to know the value of the function on the particular input instance. Okay? So they just take turns. So there's a protocol that they decide a priori, and as Alice is unbounded, Alice can send any function. She can compute, so A1 here is just an arbitrary function on her input. She can compute that and send it to Bob. So I'll assume for now, for simplicity, she just sends one bit. At each round, players send a bit. And then depending on what Alice sent to Bob, Bob sends back another bit to Alice, which now depends on both Bob's input and Alice's input. Both Bob's input and what Alice sent in the previous round. Okay? And this goes on for a while. So let's say they take r rounds. At the end, at the rth round, we will assume that Bob just gives out the answer. Okay? So that's the protocol. And the aim is to minimize this communication cost. So if we assume there are n bits x and each of x and y is worth n bits long, then it's trivial to see, as again Shagnik had said this, I'm just reminding you, that in n plus 1 bits of communication, you can compute any function, because Alice would just transfer her n bits to Bob, and then Bob would compute the answer, and this would take just n plus 1 bits of communication. The interesting thing is to see for what functions can we improve upon this trivial protocol, and for what functions we can't. Okay? So just to be sure that we understand the model well, here's a very simple function, parity, okay, where we can do much better than the trivial protocol, simply because Alice just sees her input and sends Bob the information whether the parity of her side is 0 or 1, and then Bob, knowing that, can very easily compute the parity of the entire input. So this just takes 2 bits. So parity is very easy. We can do much better than the trivial protocol. And if you think about it, in fact, majority, or for that matter, any symmetric function can be computed in order log of n bits, because all you need to know is how many ones does the joint input of Alice and Bob have, right? So here's an example of a hard function on the other hand. So equality. So I'm still talking about deterministic protocols. In particular, in this whole talk, I'll just focus on deterministic protocols. Okay? So equality is the function where Alice and Bob want to determine if x and y as n-bit strings are exactly the same. Okay? And if you think about it, it seems like you can't do anything better than Alice to transfer her entire input to Bob, and then Bob compute the answer, which takes n plus 1 bits. And one can show that this intuition is correct. It takes an argument, but it's not hard. Okay? It's a fun thing to prove. Okay, so now I want to change gears. So that was about two-party classical communication complexity. In this talk, I want to look at a particular multi-party model, not the one that Shagnik talked about, which is often called the number in hand model. In contrast, there's a sort of a weird model, which is called the number on forehead model. It's not a very natural generalization of the number in hand model, but nevertheless, it has very important applications, and therefore we'll look at this particular model for this talk. So anyways, all along I've been having the players have their inputs on their forehead. So now I'll formally say that they do have inputs on their forehead, which means what? which means that in this model, every player is able to see every other player's forehead, but not his or her own forehead. Okay, this is the strange thing. In the case of two-party, this doesn't make a difference. The number in hand and the number in forehead, they exactly coincide. Okay, but not here, and we'll see for good reasons. Okay, so I've just drawn it to be a three-party model, but you can imagine that it could be a general k-party model. And this was introduced by Chandra first and Lipton, so it's also now a classical model because it was introduced in 1983. By the way, Ashok Chandra very recently passed away. So again, unlike Shagnik's case, I'm going to talk about a broadcast model. So what he considered, just so that you don't get confused, if you happen to remember his talk, this is a broadcast model in the sense there's a shared blackboard. So what one player communicates is seen by every other player. Okay? In contrast, his model was point-to-point. Okay, so again, players take turn in terms of a protocol which is mutually agreed upon and decided beforehand. And again, what each player sends depends, as before, on the foreheads of the other player, his input, and the protocol history so far. Okay, and at the end of this, the players again should be able to compute the value of the function. And now I want to remark on these few interesting aspects of this model, which is, the first one is that if I have a three-party model, notice that every pair of bits is visible to someone, right? Because a pair of bits occurs on at most two foreheads, so the third player can see that pair of bits. Then the second aspect is there's an overlap of information in the sense that one of the foreheads, so if I look at Alice and Bob, they both see Charlie's forehead. So they can do interesting things seeing Charlie's forehead, for which they don't have to communicate. We'll see that they don't have to communicate. So there's this overlap of information, and this turns out to be quite powerful. Okay? And as the number of players grows, so right now I have 3 players, but if the number of players keeps growing, then fewer and fewer information is missing from a player. A player is missing just the information written on her forehead. And that as a fraction of the total input is decreasing as the number of players grows. So understandably, if the number of players is large, this model can become very powerful. And we'll see it does. Okay? So lower bounds for these 3 powerful features, proving lower bounds on this model become very challenging. And as we will see, there's a reason, because there will be some very surprising protocols. They'll all be very simple, but there's, you won't, at least I didn't expect those protocols to exist. Okay, so let me just give you a very simple example showing that foreheads do make a difference. Okay, let's go back to the equality function. Now equality here is X, Y, Z, and Alice, Bob, and Charlie, they want to ensure that all 3 strings are the same string. Okay, and now there's a very simple protocol exploiting the overlap of information, the second aspect that I alluded to before. And what Charlie does is he just sees whether X is exactly equal to Y. If it is so, he says so. And then Bob compares if Z is exactly equal to X. So look, notice that this X occurs both in this. And X is the mutual overlap. Right? It's very simple, but just I'm remarking that. And if these 2 things are, even only if these 2 equality tests go through, they can conclude safely that all the 3 strings are equal. Right? So it's a 2-bit protocol. Moreover, it exploits information overlap. Moreover, if you think about it, it can be simultaneous. There's no need of interaction. We will harp on this feature of things being simultaneous. So what I mean by that is both Charlie and Bob, without talking to each other, could have sent their respective messages to a referee who has no access to the inputs, only has access to this blackboard, and still the referee would be able to give the right answer. Okay? So this shows that a function like equality, which was very hard for 2 parties, suddenly becomes easy for 3 parties. Okay? So this just exploited the overlap of information. So as I said, so therefore proving NOF lower bounds is quite hard, but there are many applications, and mainly because of these applications, this model is studied. So one of the applications that, again, I will talk about in a few slides is circuit lower bounds. Lower bounds especially for constant depth circuits, branching program lower bounds. This was the reason why, in fact, the Chandra First and Lipton paper looked at this model. Pseudo-random generators, lower bounds on lengths of proofs in proof complexity, recently data structure lower bounds, and there are more to be discovered. I'm sure there are many other situations where this number on the forehead model would arise naturally. Okay, so let me now go back a little bit to remind you about constant depth circuits, because we are studying the NOF model, especially for its connection to constant depth circuits. So this is an outstanding conjecture of Smolensky from '87, which says that majority needs exponential size to be computed by constant circuits comprising only and, or, and mod m gates. Sorry, I meant, so NOT gates are always there in circuits, so I'm not explicitly saying that. Okay, so for any m which is constant, arbitrary constant m, this conjecture is made for such arbitrary constant m, and it seems we are far from resolving this conjecture one way or the other way. It's not even known to hold for m equals 6, not even for depth 3. So in particular, we don't even know whether, forget about majority, we can't even show whether an NP-complete problem like SAT can be computed by such circuits. So ACC0 is the class of functions computable efficiently by such circuits. Okay? So what's the attack by the number on forehead communication complexity? Well, again, this is a very classical theorem. This theorem actually was first observed by Goldman and Hofstad based on this result of Beagle and Tarui. Okay? So this theorem says that every function which is in ACC0, okay, in other words, it's computable efficiently, that is polynomial circuits of constant depth, and just comprising and, or, and mod m gates, has an efficient, so here for us efficient will be polylogarithmic. Remember, every protocol has cost at most n, and here efficiency means polylog in n. Okay? So it has an efficient simultaneous k-party communication. It has efficient simultaneous k-party communication complexity for some large k. How large? Polylogarithmic in n. Okay? So every function f, so this polylog here would depend on the depth of the circuit. Okay? But it will be for every constant depth, it will be some fixed polylog. Okay? And not only that, under every possible input partition. So you can imagine that some functions would become easy if the inputs were partitioned in a certain way, and might become hard if adversarially partitioned. So this says that if f is in ACC0, under every possible input partition, this holds. Okay? So this is a very nice and clean theorem. And this obviously opens up a research direction which says, can we find such a function? Can I find a function which does not admit such efficient simultaneous protocol? If I were able to find one such, that would show that this function is not an ACC0. Okay? And this is a major goal, but we are far from answering that. In fact, we will see that my talk will try to convince you that whenever the number of players is log of n or slightly larger, the model, this communication complexity model, suddenly has it becomes very powerful, and many functions that were conjectured to be hard when the number of players is large, we will see actually turn out to be easy. Okay? So here's a conjecture that I want to say, and to state this conjecture, I'll talk about composition of functions, and I don't have to tell you the virtues of composition, because in the last talk we saw composition. I think also in the talk on CSPs we saw composition. So it's composition in that style. So now I have two functions f and g. They are composed with each other, where f is a function on n bits, g is a function on k bits. Okay? And how do you compose f and g? So you view the input of f composed with g as a k by n matrix. Okay? It's a very natural view. And then you apply g to the columns of this matrix. The columns are k bits long, right? So you do that, and then you evaluate G on every column. There are n columns, right? And then you get this resulting n bits, and then you apply f on that. Okay, so that's f composed with G. It's a very natural definition. And the way the inputs will be partitioned, so the input I'll keep viewing as a k by n matrix, the way it will be partitioned, the canonical way we will partition it for the players is that each row will be held on the forehead of a player. Okay? So a player will just miss his or her corresponding row. Okay? And the question that we want to understand is, since majority has been conjectured to be outside of ACC0, we'll look at the complexity of majority composed with majority. Okay? So what is majority composed with majority? So you want to see if the majority of columns, I'm just restating it, if the majority of columns are columns where the number of bits set to 1 is at least k by 2. Okay? So that's majority composed with majority. And if you think about it, I mean, any such composed function, it seems like, especially for a function like majority of majority, it seems that, well, the only way that the players can compute this is to compute separately each column, right? Okay, and if you do that, then obviously you will have to, the communication complexity, it would be n times the complexity of computing one majority. Okay, and it's not hard to convince oneself that on average you will need obviously 1 bit of communication for computing one instance of majority. So based on that, there's a very tempting belief that, at least the simultaneous complexity of this function, where there's no interaction, deterministic simultaneous complexity of this function should be, well, super logarithmic. I mean, it seems like it should be at even n, omega n, but certainly it should be super logarithmic, right? Seems like a very reasonable conjecture. And if this conjecture was true, then, as I said before, majority of majority would not be in ACC0, right? By this theorem that I just said. Yeah.
So this model, when you are saying that, are you assuming it's number in hand or number?
No, number on forehead. In this talk, we're only talking about number on forehead. Okay. So that means, as I said, you have the inputs. Each row is placed on the forehead of a player. So a player is not able to compute one column because, if it's the first player, she misses this particular bit. Okay, so she can't compute G without the help of others. Okay, and a balanced function like majority, if the inputs are adversarially chosen, you still don't know whether, that one extra bit can swing the value of the answer. Right?
So, sorry.
What was D?
Oh, D is for deterministic, K party simultaneous. Right? K for K players simultaneous. So, if this...
For a number on forehead model like majority, so, it should be easier, right? Under the fact that you're missing only one person's information.
Yeah, well, that's true in general about a number on the forehead. You're only missing one bit. But the point is, if the inputs are, how does this particular player know the value of evaluation here? Because the first player, let's say, is missing this first bit. Right? So what is your intuition about?
Majority itself is quite easy. It's just composition in this way.
Yeah. Of course. Oh, just majority would be easy, as it was easy for 2 players.
Yeah, so
but
what we're confusing is you said Smolensky's conjecture is that majority is not ACC0, and therefore.
I'm just coming to that. Okay, that's right. The next line will be that. Okay, so majority composed with majority would not be in ACC0 if this is true, right? And this would imply that majority is not in ACC0, right? Because if majority is not in ACC0, if majority were in ACC0, how could majority of majority not be in ACC0, right? So this actually shows a path for proving that majority is not in ACC0, although majority by itself is an easy function, but this composed function is hard, and therefore this gives a path of proving majority is not in ACC0. And this conjecture was proposed by Babai, Kimmel, and Locum back in '95. Unfortunately, this turns out to be false. it's just, yeah. I mean, when k is very large, as we will see, this model becomes very powerful. Okay?
So what's the difference of k on the right hand side? It's believed to be.
So if I knew that for any polylogarithmically large k, this was true, then
the chain of implications follow. But what was the conjecture
that for any polylogarithmically large k, this is super-logarithmic. That was the conjecture. In fact, they had conjectured, n to the omega 1. Okay. The original conjecture was that. In fact, they themselves proved this to be wrong. Okay. In a subsequent paper. Okay. So now, so I'm going to talk about various. So I just motivated this question with ACC0. Now I want to tell you about some very interesting upper bounds that were known. Okay. So remember this is important. This aspect that this is simultaneous is going to be an important thing in this talk. Okay. So what were the upper bounds? So now we're going to look at upper bounds for composed functions. Now here are some functions that have been traditionally looked at in communication complexity. Generalized inner product, which is just a natural extension of inner product. Inner product is, you have two n-bit vectors. You take their standard inner product mod 2, okay, just to make it Boolean. And generalized inner product is now you have k vectors, right? So you take so it's naturally expressed as a composed function. You take the and of each columns, right? And then you look at the XOR of that. Okay, so that's generalized inner product. Set disjointness. That's, again, a very important function in communication complexity, where you basically want to see if there's an all one column. So that, again, is a composed function because it's an OR of AND. Right? So these are all composed functions. And way back in 91, Grolmus showed that all these functions, which are super hard for k equals 2, and in fact, even now we know that they're even hard for small k, they suddenly become very easy when k is at least log of n. Right? The communication drops down to log of n, polylog of n. Right? But these protocols, so this was known, but the interesting thing is what was not known is these protocols were inherently interactive. There was a very key step in which interaction was needed. Okay? So they were almost simultaneous, but not quite simultaneous. Okay? And the hope was that if we just focus our attention to simultaneous protocols, maybe these functions still remain hard. Okay? So in a very interesting paper, Babai, Gal, Kimmel, and Locum. So I guess, so the previous paper did not have Anna Gal. So this paper had, this is a follow-up work. So they showed that in fact all these functions, they have simultaneous efficient protocols. Okay, but these functions, what they showed is that what's special about these functions is that the inner function g belongs to a class called compressible and symmetric functions. Okay, I won't go into the details of what is compressible. Symmetric is clear, but what is compressible, I won't go into there because of a lack of time. But the point is, these are very special functions. A random function is not compressible. Okay, but as k becomes larger and larger, notice that the choice of functions that you have for the inner function also grows, okay, doubly exponentially in k. And what they showed is a very small fraction of those inner functions turn out to be easy, okay, easy even for simultaneous protocols. Okay. Then in 2012, along with Ada, Fauzi, and Nguyen, what we were able to show is that one can relax this restriction. It turns out that for actually any inner function, this function becomes very easy, okay, provided you have enough number of players. Okay, and this work basically combined the ideas in these two papers. These were different style of protocols, and one could combine them in a precise way, and then you can show that this result follows.
Is there a reason why for k equals 3, for example, is there a specific function which requires communication complexity simultaneous? No, I'm just wondering the addition of k that is at least log n, is that an artifact of the proof?
No, for k equals 3, we know that these functions are hard. No, it's important that k be larger than log n. The interesting thing is, again, so I remember I had a list of three aspects of this model. So all these so this protocol, this first one used the feature that less and less information is missing. This protocol used the feature independently that there is a large overlap of information. And what this protocol does is it basically combines both these ideas, both these aspects. That less and less information is missing, and there is a large overlap of information. The two taken together can be made simultaneous. It's not surprising because the protocol that I showed you for equality, which was simultaneous, also exploited the fact that there's a lot of overlap of information.
So these are DSIM K upper bounds.
DSIM K upper bounds, right. Okay, so the next line of attack was basically the following. What happens if we do block composition of functions? Rather than composing just one column, now we are going to look at a block of columns, right? R columns. So the inner function now acts on R columns. Okay. And so this is just an example of such a function. So I'll denote GR, where R will mean that there are R columns involved for computing G. So here's an example of R equals 3, N equals 2, right? So that's the definition. That should be clear. Okay, and the conjecture, the next conjecture, in fact, this conjecture is also due to Baba et al., which says that the simultaneous complexity of majority, now this is the inner function now acts on root n columns. So there is, the outer majority is also on root n bits, the inner majority is also on root n number of columns. That should still be hard. Okay, again notice that this would imply, just as before, majority is not an ACC 0. Okay. This is still open, and it's open even for interactive protocols, meaning, not only do we do not have any efficient protocols simultaneously, but we also don't have efficient protocols even if I relax simultaneity and allow interaction. Okay, so it's even open for interactive protocols.
Earlier it was for any n and any case, so wouldn't this be a special case?
Sorry, I'm not following. What do you mean by earlier?
So they disproved this theorem.
No, they didn't disprove this. What they disproved was if this was 1 and this was n, okay, that got disproved. Okay, so if majority was just acting on one column. Okay, so what our result here is that what happens is if you have any inner function on R columns, it has not a simultaneous protocol, we still don't know. It has a 2-round k-party deterministic protocol. Okay, so the interaction is very mild of this much cost. So this is a little bit of a mouthful. Let me just say what it means. So if you notice these numbers, if R is about order log of n, so the number of blocks involved is about order log of n, then the cost is still polylogarithmic. Okay, and so the first remark is that this is the first protocol for R greater than 1. All previous protocols were for just inner functions that acted on one column. The second thing is, notice that if you take if you compose majority acting on S columns with any outer function, this is in the class Fn composed with some function over log of S bits, right? Because you can replace the S columns by the count of ones, each row by the count of ones appearing in there, right? Okay, and that is enough. You still have enough information. The players can do this step completely by themselves without communicating. So this lies over here. Okay, and this theorem along with this observation just shows that majority composed with majority of R has efficient protocol when R is polylog. Okay, when the previous result showed that when R was 1, this has efficient protocol, but now we can show that if R is polylog, we still have efficient protocol. Of course, the previous result was simultaneous. This is not simultaneous. Okay. And what are the main ingredients of this argument? Well, there is actually just one new idea in the whole protocol. The previous one, there are two things that are used. One of them has been used before, even as early as Goldman Hastad, which says that if you have a k minus 1 degree polynomial, okay, and there are k players, since every monomial is visible to some player, computing k minus 1 degree polynomials becomes easy for k players. Okay? This was known for long, but in general, you don't have degree k minus 1 polynomials. The inner function depends on k bits, so in general you don't have degree k minus 1 polynomials. But what we showed here is that the new idea is that you can do this degree reduction by changing bases. So let me try to quickly, since I don't have much time, let me just try to, I'm going to skip this particular slide. It shows the old idea why low degree polynomials can be evaluated by k minus 1 players. Okay, so this is a simple idea. Okay, but now let's look at how, in general, we are not going to have degree k minus 1 polynomial, so what are we going to do that? So let me just set up the polynomial setting. So you have an inner function g which depends on k bits. So notice that every inner function, every Boolean function can be expressed as a polynomial, right? And the degree of that polynomial is at most going to be k. So this is going to be a multilinear polynomial because the function is over the Boolean cube. So xi square is xi. Okay. Now, if I express this polynomial in two parts, one is the offending part which has high degree, perhaps degree equals k, and the other is the low degree. Low degree for us will be degree less than k. Okay, because degree less than k can be handled by k players. Okay. So then, to compute this function, any such function symmetric of g over these n columns, it's enough for me to be able to compute this polynomial, right? I'm going to have one polynomial for each column, and every such polynomial has two parts, a high degree part and a low degree part. I've just summed it over all the columns. Okay. So this, as I said, can be very easily computed. This is the bad part, and here's a interesting idea that at least occurred to us. What happens? Oh, sorry, this should be C subscript I. So can we show that when k is large, okay, it would be great, for example, if this turned out to be 0 or constant, some fixed constant that is always going to be true. Okay, then obviously you don't have to evaluate this high degree part. Okay, and it is not true in general. And here we use, this is the new idea of the paper. We will show that this actually turns out to be true if you shift your basis. Okay, so what do I mean by that? So this is called the shifted basis. Okay, so suppose U is a vector, k bits long, and then I look at every shifted monomial. So the normal monomials were just the product, multilinear monomials were just the product of xi's, where I is an S for an arbitrary subset. Now I'm going to shift them by some ui. Okay, and that's called that will be called as the shifted basis. Okay, and it's not hard to see that for every such shift you still have a basis. Okay. So notice that if U is the all zero vector, then this gives the standard basis. Okay. And what we will say is U is a good basis for us, is a good shift for us, if for all columns C of A, U and C agree on some coordinate. Okay. Let me just tell you what I mean by that. So here's a matrix A, and that's, let's say this is U, one example of U. I claim that this is good. Why is this good? Because on the first column, this vector U agrees on these two coordinates. It just needs to agree with one coordinate, whereas it is here agreed with two coordinates. Similarly, for the second column, it agrees with many coordinates. And if you see that in every column, it agrees with some coordinate. Okay, which by our definition means that U is good. Okay, and here's an example of a bad U, because this does not agree on any coordinate with the second column. Okay, so this is just to illustrate the definition of what I mean by a good basis, a good shift. Okay, so why is good good? Okay, so it's good for the following reason. So remember, I need to evaluate that thing on the right hand side. I apply this U shift for a given U, and this U shift can be computed by the players themselves. Okay, so they all know this right hand side that they need to evaluate. In fact, they know this therefore for every possible U shift. So if U is a good basis, then what happens is this high degree thing zeros out, right? Because for every column, there is some coordinate on which U agrees by definition. And so therefore, the high degree part just vanishes if U were good. Okay, and that's why we have called U good. Okay. So the point is okay, but how do I guarantee that the players will be able to compute a good shift? Okay. And it just turns out by a counting argument that actually good shifts are plenty. Okay. If you take a random U, it's going to be good. Okay. So this is very simple to compute because you just compute the probability that U is bad and the probability that U is bad. So let's say we're looking at the point of view of the K players who's able to view all K minus 1 foreheads. Okay. And the probability that a particular column, if I choose a particular U, a random U and a fixed column, what's the probability it's going to be bad? It's going to be bad if it disagrees with every bit in that column. So that's 1 over 2 to the K minus 1. And then just apply the union bound. So if K is large enough, this is going to be small, right? And so basically if K is slightly larger than N, a random U is always going to be good. Okay? So therefore, the player K can announce a shift, okay? A good shift U, and so this is the only part where this part to announce a good shift U, you need interaction. So this is the only non-interactive part. Once player K announces a good shift, all players compute their portion using the shifted basis. Okay. And so the cost of that is K times log of P plus the cost of announcing this U shift. And U is a K minus 1 bit vector, so it just takes K minus 1 bits. Okay. And so I showed it for simplicity with just R equals 1. But the point is this polynomial idea easily extends to larger R, order log of n R. So you just have to, if you're surprised at why is it log of n, talk to me offline, I'll tell you that. Okay. So there are various possible questions to look at. The most obvious question, the most obvious question I forgot to mention is that, can I get rid of this interactive part? The first part says you still require one player to look at all foreheads and compute a shift. Is there a way that you can avoid that? Okay. So in other words, to make the protocol simultaneous, it's currently barely non-simultaneous. So the other direction is, can you improve from log of n to order log of n? Okay. And then the other question is very related to this. So remember the old conjecture that is still outstanding is what happens to this particular function. Now, if we can improve the protocol to order log of n, that's enough to disprove this conjecture, right? Because, as I said, if you have majority of S, it is in any of log of S. So if I can improve all the way to order log of n for an arbitrary function, that will allow me to get an efficient protocol for this composed function. Okay. Yeah, thanks.
Is there any intuition about why our K minus 1 degree polynomial can be computed easily by K players?
Yeah, so it's actually very simple. So any monomial has K minus 1 variables, right? So as I said, so every K minus 1 foreheads is visible to some player. So the players can partition the monomials beforehand among them. And each player is responsible now for a monomial, so he computes his sum of monomials and announces. Right. So it's a simultaneous protocol.
Any other questions? Okay, let's thank the speaker.